Picking up right where we left off. So I'm starting off on this slide right here, again, to remind you of this Heisenberg uncertainty principle and Schrodinger's wave equations. So again, this idea that because electrons are both particles and waves, it's very difficult to know their position or their momentum simultaneously with any arbitrary level of precision. So instead of orbits, we use orbitals, and that's what we're going to be talking about in this next video. And an orbital it's a mathematical solution to the Schrodinger's wave equations, okay? But this mathematical solution, it's a three-dimensional mathematical solution. So these orbitals are shapes, and what they represent are probability distributions or regions where you will likely find the electron. And again, we start by noting that the higher the value of psi squared, this probability value, the more likely it is to find it. The lower the value of this psi squared probability, the lower the likelihood that you will find the electron. And where we're talking about finding it, we literally mean in this radial position as indicated in this graph right here, okay? So let's see. So the first one we're going to talk about are s orbitals, okay? So we noted for an s orbital, you have to have L equal to 0. And we can have s orbitals for n equals 1 all the way down to n is equal to 6. We can go all the way up to 6s as long as L is equal to 0. Okay? And so these s orbitals end up having a spherical geometry. So for now, let's just pick on this 1s orbital. Okay? So we have these two equations here that we're going to talk about. So total nodes are n minus 1. So that means 1s has 0 nodes because 1 minus 1 is 0. So an s orbital is literally just a sphere, okay? And within that sphere, within that three-dimensional sphere, that represents the probability of finding the electron, okay? So for example, if my nucleus is right here in the center of that 1s orbital, then it is likely to find the electron anywhere in this orange region, okay? So I have a really cool computer simulation I want to show you. So this is for my CHEM 362 class. And they solved the Schrodinger equations using this Mathematica program. So I'm going to also be sharing with you some of these results here. And so you can see all the equations and stuff. You don't have to know all this stuff. You don't have to know this code. It gets pretty nasty. But here is our 1s orbital. So it just becomes a sphere, okay? So for example, if we had a 1s electron, it could be anywhere within this sphere. Anywhere within this three-dimensional object represents the likely places of finding that electron, okay? So now what about all of this node business and the 2s and the 3s and all that stuff? What does all of that mean, okay? Well, total nodes are n minus 1. So when we go to 2s, you can see that we have one, let me write this a little bit better. Okay, so I'm just going to say here this number that I'm referring to is the total number of nodes. Okay, and so we recognize that 2s has one total node. Okay, so what kind of node is it? Well, in terms of nodes, we have radial or angular. Okay. And they both have to add up, so I'll actually say, I'll erase that once again. So I'll say radial nodes and angular nodes, and radial plus angular equals the total. So you can see I've got an equation for the radial nodes right there, n minus 1 minus L. Okay, So here this is total right here. And then now we can calculate the radial nodes. And so obviously for the 1s, it's going to be 0. But what about 2s? Well, if it's 2s, L is equal to 0 and N is equal to 2, right? So that becomes 2 minus 1 minus 0, which means 2s has, I ran out of room here, 2s has 0 angular nodes, but 1 radial node. What is that radial node? Here it is, okay? So technically, that's a radial node, and it's radial because you can see it's based on some mean radius, right? I can draw an arrow, and that represents the radius of that node, okay? So what about 3s? Well, we recognize that 3s has got to be 2 minus 1 to give me 2 nodes in total, okay? So it's going to be 3 minus 1 minus L, which is also 2. So all of those nodes in 3s are radial nodes, and you can see here they are, 1, 2, okay? Well, what if we were to do 4s? Well, as you might imagine, 4s should have 3 total nodes, and all 3 of those are radial. So that means 4s, we would have, 1 node, 2 nodes, 3 nodes, and even a 4th node. And so I know my picture doesn't look very nice. But now what these nodes mean, okay? So this picture that you're really seeing here is a cross section, all right? So from the outside, a 3s orbital will still have that spherical shape, okay, from the outside. But if we were to slice it, if we were to slice this in half, right, that gives us the cross section. And what we would see is like these little onion layers. And the white regions, okay, those are the nodes. So that's where there's 0 probability of finding the electron. So a node equals 0 probability, okay? And so what this orange represents, so I'll draw an arrow to the orange region, that represents probability. And I'll even go on to call that finite probability, okay? So another way we could view those pictures are like the following. So if I look at now all of these little dots, okay, those little dots are kind of like the shaded areas you were seeing before. So let's say dots represent possible electron positions, okay? So if we did these calculations hundreds or millions of times, all of these little spots represent probable electron positions. And what is observable, what you will notice are those kinds of onion layers. So for example, if we first start at the 1s, we can see there's no internal radial nodes, okay? So in other words, if I made a 2-dimensional graph out of this shape, it would just be one really large peak, and you can see that peak corresponds to where the electron density is the highest. So that gives us the most likely place to find the electron. And you can see if I trace where that peak is, it's something like maybe, I don't know, 100 picometers away from the radius, or away from the center, right? So if I looked at the center, that most likely place is like somewhere right here, right? So it does kind of look like an orbit, but because it makes this 3-dimensional shape, we call it an orbital, all right? So that's due to n is equal to 1, L is equal to 0. So now if I go to 2s, n is equal to 2, L is equal to 0, that gives me, remember, 2 minus 1 minus 0 equals 1 for 2s, okay? So now there's that one single node. There it is, okay? And it just so happens to be a radial node because of this spherical radial geometry, all right? And so here you can see that node right there. It's kind of tough to see it on the picture, but right, you can see where that gap is, where there's no electron positions. That's what makes up the node, all right? And so now when we go to 3s, right, 3 and 0, 3 minus 1 minus 0 equals 2. And so there's my 2 radial nodes, okay? And you can see they're given by these areas, these regions of no electron density, all right? And what you also notice, based on the height of the peak for 3s, that's the most likely position. For 2s, that's most likely. And you can see for 1s, there's only one peak, so that's the most likely place. So the other trend that you should observe from this is as we go from 1s to 2s to 3s, they get bigger, okay? So going from 1s all the way to 6s, the size of these orbitals are getting bigger. So we're predicting that the atoms are getting bigger because those electron densities are getting further and further away from the nucleus, okay? All that being said, look, there is still some, I'll say still some probability of finding those electrons in the inner layers. It's not 0, but it's still smaller than the most likely position, okay? So it's still somewhat finite, but the most likely positions as the orbitals get bigger are to go further and further away from the nucleus, okay? So let's move on